host, Dr. Gossett, and I'm really delighted to be here to initiate this festival. It's a great honor. Great honor to be in the new building and the auditorium for the first time as well. So I'm going to talk today about something I've never talked about before. It's honing to the theme of the festival, trying to understand humans, perhaps, within the animal world that we belong. At first it seems odd because I'm known for collecting dinosaurs. What does that have to do with humans, after all? Well, oddly enough, I've taught human anatomy to doctors here, would-be doctors, including the one that became a pediatrician of my children here at the hospital. Because, in fact, anatomy extends far beyond our humanness and deep within the animal realm. In fact, the history of life, writ large, is written into our genes, and it's deeply embedded in our anatomy. And what I hope the take-home message from today's talk is that, yeah, we can learn a lot about humans by looking back in time and seeing where we came from. And even more powerfully, after great extinctions like this one at the end of the Cretaceous, when life takes a different turn, what do other animals that have inherited the surface of the earth do with the anatomy bequeathed to them? That's really this theme of my talk. We're going to compare humans and our mammal brethren to dinosaurs and their reptile brethren. That's what I'm going to do today. Of course, dinosaurs literally did not go extinct with that asteroid. They flew off into the sunset about halfway through their evolution and survived that extinction to be with us today as birds. We know that quite from an enormous amount of evidence. They radiated for 150 million years across all the land masses, migrated on a path that we would later take across Siberia into Alaska and down into North America and back. An amazing story. They didn't burn as much energy as we did cell by cell, so they could reach sizes like this as herbivores. To find that story has been the adventure that attracted me to my discipline, paleontology, in the first place. It's an incredible adventure. This is an expedition that I led crossing Algeria's desert. You got to take people that are ready for adventure, have that spirit. And what I did is I took people that had never seen the Sahara, much less crossed it, because I knew these were the kinds of young kids that would, in fact, carry me on an expedition that can be trying. You don't bring a non-digital, thermometer in the field, otherwise you'll never know the true temperature. But it's mental as much as physical, definitely. And I'm a player coach. So I lead by example. I enjoy the challenge of going somewhere where no one quite has been before. And that's why we make so many discoveries every time. We have tons of material that is calling me every night and will be announced in the coming years. But it's a stellar team like this. I mean, there are students standing on top of those cars that are now professors at different places in Canada, the United States, and so on. Doctors who took time off to keep us alive, et cetera. Amazing people. Now, my story sort of begins here at the university when I began to take a look at the little Eoraptor skull from the origin of dinosaurs. This is a skull that I found down in Argentina because I decided when I came here to the university that I would go back to the origins of dinosaurs if I was going to study this group. I wasn't wedded to dinosaurs, and sure enough, more discoveries followed. This is Eodromius. I'm going to talk a little bit about my research before I head into the main themes for the talk today. You probably haven't heard of Eodromius. It was announced just a few years ago. That's the Badlands in Argentina, right near the border of Chile, where these finds were made. It's an enormous and gorgeous area. And putting these animals together and really taking a new look at the origin of dinosaurs is one of a whole series of questions that we have for this very interesting group. Where did they come from? How did they dominate? What was the dinosaur like? Was it four-legged? Was it two-legged? These are basic questions that we were able to answer. Was it a predator or herbivore? I've subsequently worked at the later stages of dinosaur evolution, a period often mispronounced the Cretaceous, but really it's the Cretaceous. It's the last great period when the continents had begun to drift apart because the story of dinosaur evolution is inextricably mixed up with the Earth's evolution of the continents. It was the era of breakup. The mammal era succeeding is the era of reconnection. And so trailing these dinosaurs around the world has been great fun. That's a parrot-beaked dinosaur from Inner Mongolia. This is a sauropod from Africa, from the country of Niger. Nigersaurus is what I named it. Putting these things together requires an enormous amount of work, both taking the bones out of the ground in the field, transporting them halfway around the world, preparing them out of solid rock like sculptors. You see how thin that bone is? You can shine a light right through it. That's one of the cranial bones in this dinosaur. They were spread through solid sandstone. This is actually the first prototype dinosaur skull. We make regular trips to the hospital at times when humans are not there in the scanner to subject our dinosaur bones to the scanner. And also high-intensity scanners for smaller things. And then we reconstruct, and we are now in progress, actually, you're going to hear about it next year, in creating the most accurate digital dinosaur. It's going to be a reconstruction that is, it lives not by the sculptor's hand when you're adjusting missing bones and the like. It's entirely digital in a computer. We're going to move to mounting that dinosaur from a completely digital model. It really is a new era that we're working within. We can look inside skulls like this to the endocast, the brain cast. That's a space filled with stone inside the skull that house the brain. We can go even further and look at the tiny little canals that operated the organ of equilibrium to tell what the habitual posture of the head was. And we can go on to do other things digitally, including, as I said, reconstruct dinosaurs. We find large and small dinosaurs. One of the themes of the talk that I'm going to be emphasizing today is we all have a pretty good idea what dinosaurs, especially the younger kids in the audience, Triceratops, Brachiosaurus, more than I can teach my college dinosaur science class, quite frankly. But what I try to teach them that you might not know as well is how these fit together and what happened over time. Because it's really interesting. Some interesting facts, for example, are that there's no truly aquatic dinosaurs. Did you ever think about that? Don't confuse the plesiosaurs and the sea monsters. Those are other kinds of reptiles. There's no dinosaurs that hung around in trees like our ancestors did at good body size. Yeah, they eventually flew into the trees before the Mesozoic was over, but that's different. There's nothing like a primate. I'm going to argue there's nothing like a wolverine, which is a digging mammal, of which we have many different kinds, including some that hang out on our campus. Opossums are pretty good. They also climb. So it's really what was in these spaces. When you begin to think about it, you realize that their world was a very different world. I'm going to argue that fundamentally, and this is new, I'm going to argue that fundamentally they moved in a completely different way on four legs. We know how birds on two legs move on the ground. We can watch a chicken. And we argue that Tyrannosaurus rex and other two-legged dinosaurs pretty much operated like that. It took us a long time to stop mounting them like in our own image. Their back should be horizontal like a bird, just like the mount at the Field Museum. And despite some differences, physical differences in weight and so on and so forth, they would have moved pretty much like a bird. What about the four-legged animals? Dinosaurs, many of them are four-legged. I'm going to argue today that they moved entirely differently than mammals today, and that this is a fundamentally something that happened early in their evolution that literally constrained what they could become. We're going to find out that mammals, including humans, are likewise constrained to be what we became in some important ways, what we did not become. Sometimes it's an advantage. Sometimes it's a disadvantage. Strangely enough, I hope some of you might have seen the documentary Skeletons of the Sahara that aired last week. It was in this place, very good. It was in this place that while looking for dinosaurs and crocodiles, we found the largest archaeological site in the Sahara, of pre-Egyptians from 5,000 to 10,000 years ago, and a human story and drama that is just unbelievable. It really is the story of humans in a green Sahara prior to the rise of civilization in the Nile as we know it, the rest of history. Amazing. Pre-adapted, perhaps, having taught human anatomy to recognize human skeletons, be able to excavate them. I was really thrilled to change my direction of research for the time being to archaeology from paleontology. And it's that perspective that I want to try and bring to you today. Looking at humans, looking at dinosaurs, I work with many students to create the animations in that film. This, a skeleton from 9,500 years ago, scanned in our hospital and then made to stand again. They didn't mention this in the film. We actually worked on a new way to calculate human stature via CAT scanning of intact skeletons with this work. Pretty amazing. Stood again. Now, today, I want to try and spend the rest of the time, in a little bit hurried, Vertebrate Anatomy 101, 3 or 4 slides. The Great Divide, mammals versus reptiles. Mammals, innovations and constraints, we'll look at ourselves. Reptile innovations and constraints using, in particular, dinosaurs. So when we look at vertebrates, we have to realize that we all came from an aquatic background, ultimately, with fins, with internal bones instead of limbs. On our faculty, we have someone who found beautiful transitional fossil. And this is sort of an engineer's diagram of what happened when basically a fin and an animal powered by the tail in the back connected to the structural support of the body in the center of the body. That's very handy. You got the propeller at the back end, and it's attached directly to the structural support of the animal. Now, you want to come up on land, and you want to move with these things sticking out of the sides of your body. Very different situation. What happened at the back end was very simple. Let's take some bones and attach it right to the column. What happened at the front end is going to be our story for today. Totally different situation. We got gills, all sorts of arteries and stuff, and we can't reach in and connect. No, instead, we're going to connect it to the next best thing, which is the back of the head, and maybe down around the ventral side to something we call the sternum. And that's what happened with the forelimb. It's really important because what happened in mammals, what happened in reptiles, is a big fork in the road. Okay. If we go on to look at, this is what is in the way. Gills and feeding and breathing. And still half of vertebrates alive today use this mechanism. Half of the species are like this bowfin that we can find in the rivers. And they've got gills to breathe. And when you look deep in the embryonic history of any vertebrate, such as a human, diagrammatically here, you find a little embryo like this. We don't have functioning gills, but we have the architecture of breathing like that. That's where our anatomy begins, okay? And so when we find fossils of this actual transition back 300 and 300 plus million years ago, we find the hind limbs attaching to the axial column and the forelimbs attaching to the back of the skull or around to the ventral side. And the limbs sprawled out like this. And what do animals do when they come up on land? Well, let me go back. They swim. If you ever see a salamander or a lizard, they swim on land. They twist their body as if they were swimming side to side. And they push their legs forward like this. That's what they do. They swim on land. But that would only go so well. When you want to move fast, you got to change the whole dynamic. You got to move up and down like this cat. You got to bring the legs up and under the body like a cat and independently like a dinosaur or a bird. And that's ultimately what happened. I had the incredible luck to find this mouse-sized animal. That's less than an inch. And this is my first fossil. I found it in outer Mongolia, of all places. And in it, preserved this beautiful drawing, just, it's 1 inch across the entire drawing. That's how small this was prepared out, is the beginnings of what happened to the shoulder architecture of mammals to allow them to walk upright and move like you and I know they do, because many of you have pets. How do they move? They move with hinge-like elbows, not corkscrew elbows from walking outside like a swimming animal on land. They move like this, and they move with elegance. This is a reconstruction of that little mouse-sized animal. And we can look further through X-rays to something like a primitive mammal alive today. This is an opossum. The actual shoulder becomes mobile, and it moves. Our shoulder is mobile. You can feel it move. It's connected only through the clavicle. And in these mouse-sized animals that invented this 80 million years ago, they weren't thinking about gaits and all sorts of things like that. But when animals started walking upright with this, they realized it was probably for flexibility. They realized all of a sudden they could do things that no dinosaur ever conceived of. It was as if this jury-rigged shoulder, which is connected only by a clavicle and mobile, something you want to actually power your body with, was all of a sudden like a four-wheel suspension system. The shoulder joint is moving all over. Look at the head of the herbivore and the carnivore, flat as a table. They're going 40 miles an hour around a bend. How do they accomplish this? The shoulder moves to physically change the length of the leg. It also operates like a suspension system. And so you see both. This is what a mammal runs like, beautifully, like on a suspension system. Now, we humans, this is Usain Bolt, we humans have adapted this to two legs remarkably. I want you to look at the slow motion that's going to follow this. At the fastest speed a human can run, some 20-odd miles an hour, 23, 24 miles an hour. When you see the end of this videotape, I want you to look at his head. It's flat as a table. We've been able to do this with our hind legs because, in fact, we were built to run. Humans are truly built to run. I want you to look at the slow motion here. When his head running along the stadium, he's running as fast as he possibly can, and maybe his head is moving 3/4 of an inch or so. It is totally amazing. And we actually change our gait when we walk going up and down to actually a suspension system the moment we start running. And we suspend like this, and we pick up speed, and we maintain ourselves later. Now, this mobile shoulder girdle is great. You see some of the incredible adaptations until you want to fly. Okay, now, a bat, flight has evolved several times. Now, a bat's got a problem. All it's connecting the main thing, the forelimb, which it has to support its entire weight and power itself through the air, is this clavicle. They make it as big as they can. It still doesn't work that well. And so they remain about this big. That's it. And they're not anywhere near as good as the other powered flyers. Now, humans have all sorts of other things wrong with them because of what they've done recently in evolution. We have taken a posture like this. Once I gave a lecture next to a leading scholar in the field of knee replacements. He was like, I can't understand why the knee is designed that way. And after I gave my talk, that the humans are not actually perfectly designed sort of in some deity's image or whatever. This is not actually, our knees are susceptible for lots of reasons for the recent postural change that we took. And as a matter of fact, just absolutely apropos for this talk, I injured and strained my back. I don't even know where or why. And it's really sore. That's how weak our lower back is from this recent postural change. And there's lots of other things. Incredible things that work well, like the Symphony of Muscles. This is a drawing for those of you who are looking at it. It's not an actual person. Beautiful drawing of the Symphony of Muscles by comparison to any other animal that allow us to make myriad facial expressions and learn these facial expressions in the first couple of years of life. We look in our throat and we see what we have done with all of those old gill arches. Okay, some of them are cartilage, some of them are bone. They do all sorts of things. It's completely jury-rigged. We got gill muscles lifting our throat when we swallow, and we have then taken our larynx and put it at about 6 years of age down, way down where I'm speaking to you from here, not up where it is in any other sensible mammal, and we therefore choke on a regular basis with food because in some crazy design, our food has to pass the air pipe. on its way to our stomach. This is not a good design, but you cannot just start from scratch. This is a crazy design. It's a competition. Either we're going to have the sounds of speech using the back of our pharynx and put our larynx deep in our throat and choke every once in a while, or forget about speaking so well. Just bark, you know. Just an amazing, amazing thing. Now, our brains are very large, and that has caused, you know, the extreme of birth in humans. So what I want to try and get you to understand is that humans, with our mobile shoulder joint and our funky eyes that fail regularly, and our bad knees and our bad lower backs and so on, are really complex organisms that come from four-legged animals that were designed to move on land in ways that a dinosaur could only dream of. Now let's look at the other side. Dinosaurs. Dinosaurs were a bipedal radiation, not a quadrupedal radiation. We are terribly unusual with regard to mammals. And some scientists, if you want to call them that, said, look, dinosaurs would look like this if they only didn't go extinct. They'd look, you know, they'd walk upright, they'd have big heads, big googly eyes, they look like they're, you know, every time we go to a different universe and a planet, there's something somehow strange. It looks like a goofy-looking human on Halloween. No, they wouldn't. This is what they did. You know, some of them have large brains. They're very agile. They communicate, some of them. Some of them even have dialects. But this is what they look like. That's one thing. You cannot predict the course of evolution very well at all. Dinosaurs did not go extinct, and this is what they evolved into. And they were two-legged, and they've remained two-legged largely. Now, dinosaurs are part of reptiles. Birds are dinosaurs, technically speaking. Dinosaurs, birds are reptiles. They're part of the reptile radiation. We don't say that. You want to go to the reptile house at a zoo, you're expecting these lower-level reptiles, but in fact, birds belong there just as much as any reptile. Now, sometimes we have to look at these because we don't have any quadrupedal reptiles alive today except crocodiles and their reptilian brethren. But when you go back in the fossil record, you realize that crocodiles, too, walked upright. This I dubbed dog croc, okay? How did it move? Well, I had to go to Northern Australia. This was an excuse to go to Northern Australia to find the only living reptile that's not a bird that is quadrupedal and can, in fact, gallop. It can take its legs into the ancestral position that crocodiles had and gallop. This is the galloping freshie of, you have to watch your fingers when you're dealing with these animals. If you show them water, they're nasty 6, 7 foot long animals, and they will, in fact, gallop. And I think that's exact. Now, look at the head. It's moving all over the place. The body is going up and down. I think this is a good model for dinosaurs in general. Why do they gallop this way? This is utterly strange. The legs together, they're not smooth. The head is moving all over the place. And the reason is pretty simple. They don't have a mobile shoulder joint. They never went through that phase that was so important in early mammal evolution. And so if we look at dinosaur evolution, in the background is dinosaur evolution, it's a bipedal radiation. Their shoulder joint never, okay, Sue is mounted wrong. Their shoulder joint never became mobile. It never separated. It's tied in the center. They cannot, when they're going upright, lengthen one leg while staying in the midline with their momentum going forward. They can't do it. It's fine if you're on two legs, like Sue. When you go down to 4, you become slow. This hasn't been noticed. There's not a single fast dinosaur as measured from the hind legs, a tibia longer than a femur. Not a single one. You know how different that would be going back to the dinosaur era than the mammal era where we have cheetahs, gazelles, and everything else that runs fast like dogs and cats? Not a single one. A quadruped. The only reasonably fast ones are bipeds. And that, of course, is not even the majority of dinosaurs. This animal is typical. Some of them are small. This is, the size of a small elephant, but even the small ones are slow. And they're slow for a good reason. They have to gallop like that crocodile, and it becomes impractical. Now, however, you want to fly? No competition whatsoever. You have your shoulder girdle. It's got all the original bones anchoring very solidly the shoulder joint, and we can't even tell if something's flying, half flying. You know, they've got the architecture, they fly. You know, it's really hard to draw a line, and we argue a lot over whether something was actually a good fly or a bad fly, or whether it was perching in the trees or not, because it was so easy for these animals to decide whether to fly or not once they had feathers. That's Archaeopteryx, the first bird. But we know now that feathers and anything bird-like that you can imagine in your head, egg laying, brooding, all this stuff evolved in their ancestors among dinosaurs. And of course, birds not only are much bigger than bats and much, well, there's some small bats this size, but there's no bat that can hover. And there's no bat that could challenge a bird for altitude or speed. They're just amazing what they can do with this original shoulder joint. And of course, pterosaurs are not dinosaurs, but they're very closely related. They took the prize for the size, as big as a small airplane. And they, too, had the original shoulder girdle. So I'm giving you some idea of what can actually constrain and channel evolution for humans as well as dinosaurs. I'm going to end there so that I believe that I'm pretty much out of time. Am I? 20 minutes. Okay. And so what I've given you is some background to understand that evolution sort of works in funny ways. It works by tweaking and adding little parts and changing something that you were using for a different function. It doesn't start from scratch. It builds onto a basic blueprint and plan. And some of the important events that happen in the course of evolution channel and guide things that happen later. We do call that historical contingency. What happened before is relevant to what happens next. We still can't tell exactly which way evolution is going to go, but we can say some things about where we've been and what seems to be possible and what seems to be impossible. And I've given you a few examples from dinosaur evolution and the evolution of mammals and humans to try to relate us humans to other animals. I'm going to open it up for questions. I'm sure there'll be a lot of questions and maybe even some objections. You never know. Maybe some answers. Thank you very much. So we got questions. There's one up here. I guess we'll be cycling around with the microphones.
Yeah, no, he needs 50.
Yeah.
I'm just wondering, how do you know that leaping or galloping crocodile, how do you know how old that is, that you're likening that to a quadrupedal dinosaur?
You mean the drawing or the living animal?
The living animal.
The living animal is, I'm not sure how old. It's alive today. It's a freshie. They go back, several million years. Yeah, they go back several million years. There's a point, now crocodiles are unbelievably amazing. They are the only four-legged animals, either reptile or mammal, that came up on land. And as you saw by a lot of the fossil examples, I have many like dog croc, boar croc, others. They were upright and running, pretty much like mammals were. And they went back to the water and learned how to swim like a fish. And recent people, scholars, who don't know the fossil record have misinterpreted that as lizard-like or fish-like. In fact, it has nothing to do with that. They involved a muscle in their tail and a way of locomoting like a fish. So the amazing thing about that galloping crocodile is it gallops, then it goes in the water and swims away like a fish. It is the only animal alive today that can locomote in two directions with its body. We humans are perfect examples of what happens with mammals. When you're upright and moving like this, when we throw ourselves into a pool and say, use your body to swim, you swim with a butterfly stroke up and down with your body. You would never think of swimming side to side because all the muscles located now on these two sides, not on this side and this side. But a crocodile, with its tail largely, has re-evolved. It's very clear when that happened. As an aquatic adaptation to cross large bodies of water, it took a leg muscle and enhanced its tail muscles and re-evolved this. And this species of crocodile is the only one that retains, as an adult, the ability to gallop like its ancestors. There's a few juveniles of other crocodile species that do this. We cannot get an alligator to do this no matter how fast we run the treadmill. The alligator will not do this. And if you actually look at the measurements of their bones, they're about the same. So it's a mysterious thing, but it is a real look into how an animal that has a tied-up shoulder girdle would actually gallop. There's, and I think this is fundamentally the constraint on dinosaurian speed. So I don't know if that answers your question. They go back several million years. You can go through genetics and relate them. All the modern crocodiles go back into the early part of the dinosaur era. They coalesce, and they came from a common ancestor alive at the end of the dinosaur period, about 60, 70 million years ago.
My question is, if you were able to time travel millions of years into the future, what do you think humans would look like?
You know, a lot has been said about that. I'm not sure I'm an expert on it, that, you know, human evolution has stopped. But then people have said, no, that's not true. You typically marry somebody within 20 miles of where you were born. I think that, you know, we've solved a lot of our medical problems. We're going to solve more. So we're going to live longer. How could we predict it or change? Well, there's some trends that you could say will probably continue. But if you are eliminating the negative effects of some of those trends, which is what, like, for example, loss of the wisdom tooth. This is something that we have problems with 1 out of 10 times, or maybe 50% of the time. If one becomes impacted, you know, this is going to knock off somebody before they reproduce too much in times past. Now we keep everybody in the gene pool. So probably there might be a slightly slower effect of some of these things. But the main factors that still cause death in humans are still pretty implacable. They are things that we deal with sooner or later. They don't leave any mark on any of your bones. They're not related to your bones. They're related to, you know, cancer and other kinds of things. We may solve some of these things, but many of them are still in operation. Of course, many of us will die from other sorts of things as well. But I don't know if that answers your question very much. We cannot predict. Most people, even now, the predictions are wild and wildly off as to what will happen with human population, what crises await us, how much food we can produce, et cetera. People are revising their ideas over the last 20 years, and it's really difficult to understand what we are doing to the planet. What we can say is that I like to have a glimmer of hope. There are lots of pessimists, because we evolved as hunter-gatherers, just like the people I dug up in the Sahara. We evolved that way for almost all of our existence. Our genetics, our way of life is evolved to be hunter-gatherers. In low populations where you speak and you see other people and you interact with them, you fill your environment to a very low level. Now we are in a flick of a second, we are in a completely different world, capable of destroying our world, altering the climate. We have to operate sort of collectively on a global scale in a way that we simply were never evolved to do. Will we overcome it with our own intelligence? That is really the question, I think.
We have a question here.
Do some carnivores communicate to make plans of how to catch their prey?
That's a very good question. It's a behavioral question, and I think aimed at dinosaurs, because in mammals we know that some do. They pack hunt. Hyenas, for example, and so on are very good. In dinosaurs, the jury is still out. We don't know for sure. I would say yes, because they are so bird-like, and birds do amazing things too. So I would say probably, but we actually can't point a finger at a site. There's 1 or 2 sites that have a lot of theropod dinosaur bones, seemingly an unusual number. There's one in Canada, and there's one of Allosaurus. And you say, why are there so many of these predators there? Well, either it was a place where they lived, or it was a herd that got buried and died suddenly or something like that. So we have found groups of herbivores definitively. The carnivores are rare, but I would say likely, very likely. Yeah. Next.
I teach anatomy in art school, and there are 2 things I've always wondered about. One is the difference in some mammalians between an open and a closed eye socket, what function that provides if there's a divide. And the other is when I think about the human nose and the cartilaginous extension of the nose, one of the ways I've thought about it is as a breakaway protector for the eyes, that if you have a facial injury, that it kind of takes the impact before you can end up with an eye injury.
What was the second one? You're saying the
The cartilaginous extension of the nose,
Yeah.
As a protector for injury to the eye.
right.
And so comment on either thing.
Right. Well, actually, there's a lot of people studying this. I think you're talking about the postorbital bar, whether it's open or not. Yeah, and in humans, it's an important structural support. And the more chewing you do, and the more your muscles expand over the top of your head, the more compression you have here. And you can put little rosette, force vectors. You can see the forces at work. Animals who often lose that orbital thing often have massive masseter muscles that come down here, and they're really operating from the jugal to the masseter. They're herbivores typically. Carnivores usually have the reverse. They have more temporalis muscle. There's sort of a play of these two muscles, and when you get something that's away from putting stress, sometimes you can open the orbit, allows a little more mobility. I think that's the main reason. For the nose cartilage, I think, it's a curious thing. A lot of mammals have muscles on their nose, so do we. We can flare our nostrils, but you want some flexibility at the end of the nose. I think it has more to do with flexibility and closing and opening a flexible structure than protecting the face in any way. These bones are often broken. They're very thin, and so I don't know that it's protecting the face much in any mammal. There's a lot of flesh at the front of a mammal. Unlike a dinosaur, dinosaurs don't have all this facial musculature. So people put trunks on dinosaurs. Well, we have no evidence of that. Mammals are the ones with all this facial musculature for opening nose, eyes, mouth, all that kind of stuff.
So you say Sue is mounted wrong, and are you...
Oh, no.
No. I was wondering if you ever gave any thought to dinosaurs moving much like kangaroos. I'm not saying the hopping on two legs thing, but like when they go down on all fours, they do move the front legs together. Is that what you mean by dinosaurs moved slowly?
No.
Like because they
I
could
meant
move one leg apart from
that's
the other?
great. I mean, Sue, the shoulder girdle doesn't have much to do with Sue's locomotion. It's all hind legs. But the shoulder girdle should be together. We have a three-dimensional Tyrannosaurus in our labs. A gorgeous specimen died, fell over into a riverbed, and was preserved three-dimensionally with all the ribs coming around. And you'll see that the breast plates of the shoulder come right together, right where the wishbone comes, just like a bird. Okay, that's the way it should have been mounted. It was mounted differently. Doesn't have to do with the locomotion. What I mean slow is, and one good proxy is these two limb lengths, and of course the foot too, but especially these two limb lengths. They give you a general idea of the speed of a quadruped and even a biped. We have them about equal in length. When the foot and the shin bone become longer relatively, the shin bone exceeds the length of the femur, you have an animal that's less powerful, say, per foot, but much speedier. The leg is becoming longer. The subsequent joints are becoming longer. We look at dinosaurs, there's none with a tibia longer than a femur. The best are close to what we are. There's no really fast dog-like or cat-like animals of dinosaurian build or crocodilian build, and there's no reptile like that. There just isn't on land. It's upright. It couldn't evolve, I think, because if you cannot change the length of your leg to come up with the mammalian gaits that allow you to keep your head stable and move forward while you're doing all this stride activity. So you notice that any kind of mammal that's running, except a very small, like a couple of rodents, they'll lead with one foot. There's a lead foot. And then there's another foot. You ever watch a horse run? Beautiful. Okay, even with an aerial phase. Da-dum. And the head remains absolutely stable. Well, how do you do that if the body's not twisting? You got to change the length of the limbs. So dinosaurs couldn't do that. So there's no way they could run like that on four legs. So I think they were limited, and there was no speedy things to run them down except two-legged things. So that's what I mean by that they're just not anything that would have had the speed of the cheetah or the gazelle that I showed, or the agility that I showed. And I think that would show. If you visited the Mesozoic and you survived for a while, you'd see these bipeds running around, and then you'd see these quadrupeds, and you say, well, where are all the fast, small animals? And then also, where are the diggers? And where are the animals that went into the trees at good size? Because all that is related to mobility of the shoulder joint and that we have as mammals. It wasn't designed that way at the beginning. It was a pre-adaptation that allowed all sorts of things to happen. In fact, when you go to the Field Museum, you look at a mounted skeleton elephant, realize there's nothing connecting this limb, these two limbs that are holding 60% of the animal's body weight, to the body, except the clavicle down to the sternum. Who would design something this way? It's crazy. And yet, it was an evolutionary, just unbelievable innovation.
How can you tell if an animal is related to a dinosaur?
How can you tell if an animal is related to a dinosaur? Well, we start out by learning that dinosaurs increase the number of sacral vertebrae. They are like us. They have at least 4 or 5 or more. And they have a hinge-like ankle joint. When you look at the bones, those are not very satisfying answers, but those are literally the technical details that separate dinosaurs from things below. They have a hinge-like ankle joint that later became fused into the drumstick of a chicken. The hinge is built into that drumstick and its foot, and they have more vertebrae involved in the sacrum. And then from there on, there's a whole list of features. And I recommend my science paper, Dinosaur Evolution. It's a primer I wrote for high school students and teachers and students like you, where I took 3 dinosaurs and I numbered all the basic adaptations that evolved during the dinosaur era. And I think that there's many, but they include almost all the features we normally attribute to birds: feathers, brooding, a folding wing. All this is, Tyrannosaurus has a folding forelimb. Ours in the lab is preserved just like this. It looks like a buffalo wing. Just put a little hot sauce on it. Yeah.
I've got the microphone, so thank you. That was very intriguing. I have a question regarding your 3-dimensional drawing, the one that actually worked. I was struck that the vestibular apparatus looks very human-like. And I would have thought that there might be a difference in balance requirements between running at 60, 70 miles an hour and plodding along at 2 or 3. Does that not change?
Yeah, so there is. It's very subtle, actually, ironically. So now there's been several PhDs, and now that we can access these things in the fossil record with some degree of fidelity, there's a lot of interest in the exact curvature, because there's 3 little semicircular canals roughly at 3 different planes. And when you move like this, it's a very ancient system. A little fluid flow in those tubes tells you you're moving like that. And it's hooked up to your eyes, and so your eyes can catch up. It's a very ancient system, a couple of nerves connecting that sense of equilibrium to other things that keep me balanced, for example, without even me thinking about it. In the case of the dinosaur, it's pretty similar, but there are very subtle differences, so you have to actually numerically study the arc, the volume, et cetera, and people have been able to tease apart some functional differences. There are some things that characterize flying animals. For example, they tend to be larger in size and so on. But they're remarkably similar. All vertebrates have 3 except the most primitive ones. They have 2. And everything else that's jawed has 3. And very much in general, the horizontal one is roughly in the Frankfurt plane for a human, looking forward, what we call the habitual posture. I predicted that dinosaur would be face down and had a muzzle that looked like a vacuum cleaner, not facing forward like this. And when we actually did the endocast and oriented it, sure enough, horizontal, it was looking directly down. That's when the horizontal canal was horizontal. So we can use it for head posture to some extent, and sometimes for function, but they are remarkably primitive. But people are teasing apart the subtleties that give us some of the functional things that you're talking about. And especially good for flight. Sometimes it's good for head posture. Sometimes you can tell a primate that leaps versus a primate that climbs slowly from the balance organ.
We have time for one more question right here.
Excuse me, Mr. Sereno. Do you know what will life be like from 5, 100, and 200 million years from now, as in the Futures Wild documentary series?
Well, I don't know that I'd be able to predict too much. I think that we are in what is called the Anthropocene very clearly. In other words, humans are drastically changing the environment. in ways that we don't know exactly what's going to happen. We know that the water levels are going to rise. We know that climate is going to change in ways that we can barely predict. But after that, we just don't know because the world has not seen a species capable of changing the environment on the scale that we are doing so right now. So the question is, what is going to happen after that? You know, in the short run, the geography is going to be most modified by ice melting. And we can actually predict some of where this is going to go. We are still in a situation of ice ages. So in the near future, we know that it will run its course. That's a wobble of the orbit and so on, given the configuration of continents that creates ice ages. There were no ice ages in the dinosaur era. Go back far enough, and there was a completely ice ball Earth. But during the dinosaur era, the ocean circulation was much better, and the continents were located more close together. And then when they split apart, that's why we have ice ages today. So we are going to go into different ice ages again, but our effect on those ice ages is really important because it's going to change everything. So where we are 200 million years from now, I couldn't possibly say. I couldn't possibly say. The reason is, in Earth history, you can evolve all you want. And with human ingenuity, you can protect all you want. But you can't predict an asteroid and where it's going to hit. You can follow some, but there's going to be catastrophes that no human even, I think, can prepare us for. And those are often life-changing in the course of history. There are very few. You can't evolve for them. They're impossible to protect against. I wouldn't be able to say what's going to happen in 200 million years. I hope that's enough of an answer. Thank you.